actually digital because we have like a bound for the voltage that can be between 0 and 5.
Yeah.
And so then there's like a threshold of, like, let's say 2.3, I guess, that if the signal is below the 2.3 volt, it's 0. If it's below the 2.3, it's 1. So I guess the difference is that in digital simulation, you do correct, you have like a digital bound, like 0 volt and 5 volt, and you do correct it every step. So if like the voltage is like 3.3 volt, you push it to be exactly 5, because you can measure it, like you can correct for it so that always your signals are always between 0 and 5. But in analog, it's not maybe as easy to have those bounds to exactly correct and like push them to be exactly those digital bounds.
Yeah. Okay. So the just to repeat for everybody, the point is, if we do classical simulation, digital simulation is kind of clear because we define like 0 volts for 0, say 5 volts for 1. We have a threshold, and any voltage which is in between, we try to push down to 0 or up to 5. So classically, that's clean. And then classical analog simulations, people think about wind tunnels. People think about you build some kind of crazy LC circuit. And then everything's clearly analog and is only kind of maybe digitized at the end by the thing which reads out the voltage, which doesn't have infinite precision, right? So that's, yeah, so I think classical case, I feel like that's pretty clean. So in the quantum case, what do we think is the difference between these things? And so I just want to, I briefly describe these. I can describe them in more detail. But I just want to get people's sense. So I'll explain again. So in the first setup, there's a single qubit gate applied to everything, which rotates it to the right basis. And then a single laser is applied with, I believe, 3 tones. And it's run, and the strength of those tones is like analytically is like slowly changed in time relative to each other, right? So do we call that one analog simulation or digital simulation or hybrid? All in favor of analog? Digital? Hybrid? All right. Yeah, it seems pretty analog, but there is kind of this gate at the beginning. Okay, now this one in the middle from our host IBM. So they apply the magnetic field by applying a rotation on single qubits, which is the white squares. They then basically they apply ZZ-type interactions between these pairs, and on their lattice, they color the lattice so that they run them in order to avoid crosstalk. And then they basically slowly shift the value of this angle relative to these things to generate the simulation. So is that analog? Strong analog? Digital? Good. Hybrid? All right, great. So you have to argue why it's analog.
Is that the only one?
Yeah.
That's the problem sitting in the front. Okay, so I guess,
No, you're really the only one. Did somebody else raise their hand for analog?
No.
Yeah.
Okay, obviously qubits are like intrinsically like analog things. Like they evolve in a continuous state space. I think like for it to be a digital simulation, we have to leave the possible space of states that can be in being continuous. And so like classically, like we have some like distributive process that pulls you into like one of like some subspace of the spaces in the Hilbert space. I think with the quantum setup, like that's why without logical qubits, I have a hard time seeing how it can be digital, because like you still can evolve continuously through the space. So I don't think it really matters what the gates look like, or if you call them gates, like because everything is always like some Hamiltonian being turned on or off like continuously. Like they're not things in real life that just like immediately turn on or off. But I think like what makes it digital is being restricted to some like discretized space that it can evolve to.
Good. All right. So the argument is, to repeat it for everybody, is you need quantum error correction to make it digital. Quantum error correction makes it digital because it limits the number of gates, in some sense, or discretizes the error. And then I just picked, this from your paper. This is a nice example of you have different kinds of codes, 2D codes, 3D codes, no code, but you still do correction. And then you apply the same physical gate at different angles to all of the qubits. But because the code only supports certain angles, so the 3D color code, you can do T gates, so it has a plateau at S's and T's times S's. The 2D color code can only do transversal S gates, so it only has a plateau at S. You basically, that fine tuning you could do on all of the qubits is sort of lost once you do error correction. You can only live at these discrete steps. So that's very digital. So I think that's one fine definition of digital quantum simulation. Now, many people said this is definitely digital quantum simulation. So anyone want to make that argument? And a lot of people said hybrids. They feel it's partially digital. Yes?
I guess I was on the hybrid side, but they did do gates and single qubit controls, but they also mapped the system geometry and the Hamiltonian of the system to the model that they actually wanted to study. So if I recall correctly, they did basically float K, like 2-qubit drives that were just the ZX coupling of their cross-resonator interaction. So they didn't really go full programmability like digital C0 logic, and it's very much restricted to the geometry and interactions of the system in the model that they're actually able to study. But there still were digital gates and especially single qubit programmability.
Yeah, and I think I think it's kind of interesting because I do think there's like in the community, this is the rare case where you're the only person on the analog side this time. I think a lot of people are on the hybrid side because they see that you have arbitrary angle, but then you still have like discrete gates, which makes it digital. But a lot of people would say, well, that's just digital. Like as soon as I have discrete gates and I have to do trauterization, it might as well be digital. And this is just an example of when you talk to people and they tell you they're doing analog simulation, digital simulation. Take a little bit of time to make sure your definitions agree. But I think it's pretty interesting. So then the one on the far side, it does not meet the quantum error correction definition of digital. It's hard for me to think of it as analog, even though there's like this kind of analog-y VQE circuit in the middle, because it's nowhere near a direct representation of the Hamiltonian. It's like a removed algorithmic representation used to gather things about phase transitions. Good. OK. So in the first part, I basically ignored errors. And so in the second part, I'm just going to talk about errors and ways to think about fixing them just using Hamiltonians. So we basically have two main problems. First problem is that our control of the system is not perfect. And as mentioned earlier, this question about well, if you're assuming the B is stronger than J, blah, blah, blah. So that's true. We have to really think about what are possible on and off values, what are our switching speeds. It turns out that dephasing is basically our inability to keep track of time. So our inability to keep track of time of the laser or RF relative to the qubit time. And this one is really interesting. So in the intermediate break, we were talking a little bit about atomic clocks. So atomic clocks are amazing because they can keep time to a part in 10 to the minus 18. And so most quantum systems that work use not that good of atomic clock, but they use atomic clocks that are usually like 10 to the minus 10, 10 to the minus 12. because you need that as a base to make sure you're keeping time right. I also note that I believe the biggest purchaser of atomic clocks are actually computer server warehouses, the cloud, because having good atomic clocks allows you to have higher internet bandwidth because you can actually partition time into smaller slices. And then I actually heard that if we could make atomic clocks that were good and reliable and cheap enough that people would put them on the back of their flat screens TVs, everybody's internet would be faster. So you can work on that. Now the other problem is the outside world is also trying to apply Hamiltonian. Sometimes it's a classical environment. I'm always complaining about HVAC, so it's the HVAC. Sometimes it's a quantum environment. I'm on the side of atomic physics, so I try to make that very, very small. And I know we'll hear about other things later. All right. So John Pruskal had this nice phrase for quantum error correction, which he called fighting entanglement with entanglement. So I like to think about fighting Hamiltonians with Hamiltonians. Anybody seen this painting before? Yeah, where'd you see it?
I think either printed it. This is a mural, right?
Yeah, it's a mural. Yeah.
The creation of it was in a museum, maybe the Whitney a few years ago.
Oh, yeah. Great. Yeah, Whitney is pretty close. Well, actually, how far is it to walk to the Whitney from here?
I don't know, you can walk. It's like by Chelsea Market, right?
Yeah. It's nice. If you haven't been to the Whitney, it's great. If you like art, I 100% recommend it. My friend who lives here said tourists are kind of low this summer, so it was actually pretty relaxing. So, so Diego Rivera, he printed this thing. He made a big mural of it. It's called Man, Controller of the Universe. I like it because it captures a couple things. The guy's controlling the whole universe with one joystick. He has maybe like 5 dials. There are these, guys with guns causing trouble. And then I think there's this kind of unrealistic model of what's going to happen. And so that's the same. We're in the same position. So I like to think there are basically 4 types of Hamiltonians. There's the Hamiltonian we want, the Hamiltonian which is from the fact we have limited control, the Hamiltonian which is due to a classical environment. And so the important thing about the Hamiltonian with a classical environment is it can't create entanglement between your system and an external system. That's the distinction that I make. Hamiltonian from a quantum environment, which will generate that entanglement. And then we just write down this thing. And I just separate it into good, H0, and everything else is bad. So this is no problem. All I do is I just find some set of evolution such that I get out what I wanted from the good Hamiltonian, even though I have the bad Hamiltonian. Oh, yeah, I should. Can we switch to the slides I uploaded? Because I don't see a place to plug in. Oh, yeah. All right, we're good. We're good. All right. Ooh. Of course, the power cord's on the wrong side. That's fine. Put it precariously like this. How's it looking, Kavya? Say again. Okay, great. I am good. Pull the podium over, thank you. Just the other side. So the one side's internet, the other side's power. Thanks. I feel like the podium should be, anyway. Whew. All right, good. Hopefully we have power in a second. Thank you, Crystal. I appreciate it. Sweet. Thanks. Okay, great. Maybe. Okay. All right, anyway. Point is, it's impossible. So I like this. I really don't like Thomas Kincaid. I don't think there's any Thomas Kincaid in the Whitney. But yeah, sorry. If you're a Thomas Kincaid fan, I apologize in advance. My aunt loves Thomas Kincaid. I hate going to her house. It drives me crazy. Anyway, I like this idea of whatever, the Thomas Kincaid being destroyed by the empire. But the point is, there's just not enough rules, right? Like, it's too impossible. So just to like make some progress, let's start by saying, instead of having super continuous evolution, we can just have limited pulses. So I'm already basically cutting time into these small pieces. But I'm just using it as a way to simplify things. So then I can always think of my unitary. U1 is the unitary I want. V1 is the unitary that I get if I just turn on my gates, thinking I'm doing U1 and not knowing about the bad Hamiltonian. And so I can basically pull the bad Hamiltonian part through, and I get this W1, which is like unwanted evolution. And if you have a whole bunch of gates, you basically just move, right? So if I look at the end here, I'm just going to move W2 through U1 to W1. But when I do that, it's going to transform, right? That unitary will rotate it a little bit. And if I keep pulling it all the way through, we get in the blue side, all of the things we want. On this red side, we get these unwanted W's. So the good news, of course, is we control the U's. The U's change the W's. And so all we need to do is pick the U's so the W's end up multiplying up to be identity. That's it. That's the plan. It seems like a great plan. This is still impossible because I haven't put any constraints on these things. And so I don't know who to credit this to, but this is like Game of Thrones kind of dragon that's going to come through, destroy the whole city. It's terrible. But I really like, actually I'm really into art. And I like going to museums when I visit places, and I like actually going to like temples, churches, all these things. I also like religious art. And so I really like St. George and the Dragon Slayer. And so everywhere I go, I take a picture of St. George and the Dragon Slayer. I just went to Stockholm. Their dragon is awesome, actually. It has like moose antlers growing out of its head and its elbows and whatever. On the opposite side is, this is in Basel in Switzerland. And the dragon is like a little tiny dog. The dragon is so not dangerous that these angels can pull the helmet off the knight. Anyway, anybody know why the angels have pulled the helmet off the knight? How many people work at a university? Everybody? Okay, sort of. Anyway, used to. Anyway, so your university is, of course, named after famous donors. It's actually the same thing with these cathedrals. So that face is someone's real face, and they take the mask off so people could know who was the donor who paid for that part of the cathedral. Which is, anyway. So we do the same thing. We say, okay, we're just going to make our dragons small. We're going to assume they're bounded strength, they're slowly varying, life is not so bad. And then I don't know why my slides are nuts today. Also, my formatting, anyway, terrible. It's the worst. Okay. All right, good. Yeah. So one example is, you have a control Hamiltonian, which is x and y rotations. Your error Hamiltonian is z. This corresponds to basic dephasing error. It corresponds to detuning. You haven't perfectly fixed your things. I would want to do nothing. So I try to do the identity. Instead of doing the identity, I get this little z rotation. This was solved in the 1950s by Hahn using a Hahn echo. So you do identity. You do a rotation around x by pi, identity rotation about x by pi. Basically, so now I'm making it a little bit more complicated. So the z comes from the identity. When I do the x gate, I can't turn the noise off. So the x gate will also not be correct. But because I assume the noise is weak, I can maybe ignore this a little bit. Then identity z, x in this piece. I do my trick. I put everything to the far side. Operators do not commute, and so I get this eta minus a, and some changes. There's a small change in the etas. And what's great is we can, if the Hamiltonians are really small, we can add them up together. And if I want to be formal about it, I would say all of these transformations come from a Lie group. So on n qubits, it's like un, u of 2 to the n, 2 to the little n. And it's generated by a Lie algebra, which are just this elements of the Hamiltonian times minus I. And as long as things are small, the space ends up being locally flat. So I can just add these things together like vectors. So when I do that for Hahn echo, what happens is there's like a long error. There's this, I'm starting from the right and going left. There's like this B error. There's an A error. There's this different beta error. There's different alpha error. And then you're only off by the fact that that Z interaction is on when you do your pi pulse. And so I can just use this geometric picture to calculate how much closer I can get to identity. So I go from being delta away from identity, which is what this alpha is, to delta squared away from the identity, under the assumption that delta is weaker than my x rotation. Good. This is my basic example. So I need questions now before I go off the rails. I heard there was fruit to throw at me if I went too far. Could happen. Yes? Yeah, so I think this plot, so the idea is I would like to do U. I fail to do that. I do V. But I just rewrite V as what I would like to do plus something I don't want to do. So I think of this as like the unitary and the wrong or whatever. Now, every gate has that structure. But then this, there's a similar thing people do sometimes in quantum error correction called the cleaning lemma, squeegee lemma, these kind of things. But basically, I just use the fact these unitaries transform these errors, and I just push them through until they're all at the end. Now this is mathematically always possible. It's only useful if I can calculate this. Like if I don't know, if I don't know, I need some assumption about what the W errors look like in order to be able to push this through. Does that make sense? Yeah. That's right. Yeah, so what's great here This, in my picture of the geometry, alpha and beta are kind of the same length. This works when beta is much smaller than alpha. So alpha is on the order of delta, which is the unknown thing. Beta is on the order of delta squared. And so the residual error here ends up being delta squared over omega squared. Doesn't matter what delta is. So as long as delta is smaller than omega, omega is the drive of the x gates, then this helps. And that's the beauty, right? I don't have to know delta exactly. I just have to know that it's smaller than omega.
I don't know if my question makes sense, but here you have the assumption that alpha and beta are in the same dimension, right?
Yeah, so this is, okay, so yeah, okay.
They're in the, so like what if, like your qubit get lost, or like, what if somehow you have extra
Yeah, no, yeah, these are great.
freedom?
Yeah. I go back to my key point, which is if I don't know anything about my errors, I am toast. I'm toast. When I do this kind of control, I have a lot of assumptions about what my errors are like. Sometimes when I talk to my friends who work on like quantum characterization, who come from a very theory side, they hate this. This is the part they hate the most. They're like, how do you know? How do you know? How do you know? And it's like, we know for two reasons. First is, like in atomic physics, people have been doing atomic physics for a long time. Hahn came up with the Hahn echo in 1950. No one would talk about it if it wasn't useful. Like it's super useful. Because it turns out that the Z error is like the dominant error in almost all systems. And then I think sometimes my quantum information friends say, but Ken, Z basis, X basis, Y basis are all the same. Why should the Z error be so bad? And then all the experimentalists are like, it's because the Z basis is the energy basis. And it is given to us by, well, we build things given to us by nature. It is different than the other directions. By our choice, like we pick that difference. Does that make sense? Yeah.
Sorry, I guess I'm also confused about the premise a bit. So the idea is we are applying the Hahn echo to sort of minimize the residual error in some sense. So it's
Yes.
the W that we're trying to suppress.
Yeah, so I should have drawn, I don't have my diagram here. But if I just try to do identity, I end up doing this small Z rotation. And I've fixed it to be kind of delta over omega just to have like a unitless thing. That is alpha. So that's the length of alpha. So the W, if I don't do Hahn echo, is alpha long, which we can think of as just being delta long. When I apply the Hahn echo, initially these are my U's and my W's. And then I use all my W's to the end. And then because of this feature, which this feature here is that the error is small. So if the errors are small, if the errors are small, you can think of every Pauli operator as being a unit vector in a high-dimensional space. And so then I can just do regular vector addition. Well, actually, Pauli operators are always, you can always think of them as vectors in high-dimensional spaces. But because the error is small, I don't have to worry about commutation. I can just think about the addition part. And then I just, in this case, they live in three-dimensional space, so I can just draw this three-dimensional trapezoid. And then the residual part is, again, just this delta squared. Good. Okay. Yeah, so what's cool is you can do the same thing. Anyway, you can do the same thing for a quantum bath. So if I have a quantum bath where you have a z term, an energy shifting term, that depends on the Bath operator, I actually don't care what the Bath operator is at all. Could be anything. This same trick works because the math is exactly the same. And the only thing that's changed is that the Bath, the alpha axis, instead of pointing along z, now points along z tensor Bath. Now the assumption here is this happens at a time scale in which the Bath has done nothing, right? So that Bath direction remains the same direction. But that is the beginning of dynamic decoupling from this paper from Lorenzo Viola and Seth Lloyd, which it's cool because there's like kind of a direct connection to just regular Hahn echo, but it also works with the quantum Bath because we're only acting on the spin. So now you could say, well, the environment could act on all these different axes. And so then you can do more complicated dynamic decoupling sequences, which are also related to other known, like NMR methods to get rid of z. So you could do like x, y, x, y. And when you do that, it actually cancels all single qubit connections to the gate. So it could be a x or a y or a z. They cancel out across these four things. These are just early slides, but they're like a gazillion dynamic decoupling used all the time for all these things to cancel all of these pulses. Most experiments have some dynamic decoupling going underneath the hood, but you actually have a lot of choices. And so if you have to do dynamic decoupling because you're trying to get rid of error, or you have to try to get rid of controlled error, this is good. I don't have a slide on this, but I think one neat thing has to do with recently some work on logical dynamic decoupling. So you can actually, if you have logical qubits, you can do physical dynamic decoupling to push the errors down on the physical qubits. And then you can do logical dynamic decoupling on top of that in a way that commutes with all the stabilizers but gets rid of any residual error. So it's super useful. So that's great, but all of that work on dynamic decoupling is basically just doing the identity. Yeah?
Sorry, is the assumption with all of these control pulses that they are stable and accurate and you don't assume?
Yes.
Why?
Because they are stable and no. No, not to be flippant. I think the thing is you only notice your biggest error. So when you first turn up one of these quantum computer systems that have RF control, your biggest error is the Z error. And then you can get rid of that Z error by doing dynamic decoupling. Then after you do dynamic decoupling, you're like, oh man, my gates are bad. You couldn't see it before because you were just like dominated by the Z error being bad. Yeah, so that's the process. And then the other process, I still run into people who tell me quantum computers will never work. And I do think, yeah, you know what I'm talking about? Yeah. Yeah, so you talk to these people, and it's interesting to me. Sorry. The one they're always on is like, if you look at a generic quantum system, it's too noisy and it's too uncontrollable. And I'm like, yeah, but you wouldn't drive a car like that. You drive cars that work. You go to the lot and buy cars that work. Quantum computers are not systems in nature. Quantum computers are systems that have gone through a huge filtering process where all of the things that didn't work, we got rid of. And it's kind of the same here. So by the time I'm doing this stuff, my X gates are already pretty good. OK, so we can do similar things with these dynamically corrected gates. So most of the time, we have control by resonant excitation. So the baseline Hamiltonian for a single qubit looks like a Z term, which is actually the detuning between a laser and the control. And then our ability to pick X and Y by basically controlling the relative phase of basically the phase between the rotating qubit and the phase between the applied rotating field. So, we have usual problems. Power is unstable, things point wrong, polarization changes. There's lasers unstable in frequency, there's fluctuating magnetic fields. There's this problem about time relative to a local oscillator. Now in practice, because of atomic clocks, this is not a problem. Because of ways we do cavity stability, this is usually not a problem. As I mentioned before, fluctuating magnetic fields, again, when you first start in your lab, you don't see them. It looks great. Life's great. Spin echo works great. And then as your experiment gets better and better, then you start to notice the train drives by and changes the magnetic field. There's this bathroom door that needs to be changed to wood. Like the better your experiment gets, the more of these small errors you see. I think in laser-based gates, really this getting the laser intensities just where you want it to be is the problem. So when people first built NMR machines, you had this RF coil, and the RF coil would send a signal to try to push the spin in the NMR. But it was early in time, in the 50s, and they were just not that good. And so people really early started to make composite pulses, where you want to take the spin from the Z to the bottom, and you pass through Y, and you rotate around it, and you go again. And what that does is, even though your angle of rotation is wrong, it basically cancels out in the end, and you go from top to bottom. Wimpress in '94, he showed that you could actually make these sequences in a way where it doesn't matter where you start. The original NMR sequences always assume you started in the 0 state. So they would work great at the beginning of a sequence, the end of the sequence less good. And Wimpress realized you can make these sequences that work everywhere. So when I was a postdoc, Aram and I, and with Ike, figured out a way to make these arbitrarily accurate pulses. And then Guanghao Luo and Ted Yoder, they later showed how to make them way more efficient, which is the thing which led to quantum signal processing. So there's like a really tight connection between doing this quantum control and actually doing Hamiltonian design, or simulation design. So these are a couple pulses. So SK1, you want it, this case I wanted to rotate by pi/2, I go down and then around and then around. BB1, I do a few more steps. And when you think about it, the whole block sphere, it's kind of hard to get an intuition for why it works. And so I like we just do our same rule. We take SK1. These are the pulses we like to apply. I write them out. I pull all the errors to the side. And then here's where the control comes in, is I control the phase of these control pulses so that this part goes to first order to identity. And it's really nice because it has a nice geometric picture, which is it's just a triangle. And so basically, if the errors form a triangle, there's no linear part, and the error goes from being epsilon and the angle being wrong to epsilon squared. Now, I put the plus there because if you think about going around a triangle, it has an area whose direction depends on the path you take around it. If you remember from calculus 2, I guess, maybe it's calculus 3. So if you go the other way, you can cancel the area. And that was Wimpress's result, is you could go the other way, and that would lead to epsilon cubed. And so now we actually have methods, and Guanghao, Lo, and Ted Yoder's method really allows you to go to like arbitrary accuracy pretty fast. In practice, people use still basically just these two pulses. Because once you drop this thing to second order, which goes back to your point, is actually no longer your problem. And even though you could drop it to sixth order, once this major thing is like knocked down to second order, you don't see it, and you have some other problem you have to solve. You can do the same thing with the tuning. This is an NMR thing from Jonathan Jones. The NMR people gave things crazy names, so it's called corpse. But it has the same feature in being like it's just like a closed loop in space. You can compare it to, there's a different way to do these things called dynamically corrected gates that Lorenzo Viola was working on, and Daniel Ladar. And you have sort of like pulse shaping in some way to basically, again, cancel out these errors. But you can do exactly the same procedure. I just make these, I take these gates, I look at the errors, I push it out to the end. You can combine things together. There was some nice work from Japan where you concatenate a sequence which fixes the X error with a sequence which fixes the Z error, and you, again, can cancel these pieces out. So in the NMR days, Jonathan Jones showed that you could apply this, if you wanted to 2-qubit gates, because it basically depends on the Lie algebra generated by 3 anti-commuting pieces, usually at z, x, and y. But I can just replace it with iz, xy, and xx, and all of the algebra is the same. I was hopeful that we could find new forms back in 2015. But it turns out that the 2-qubit part, the xx, zz, and yy, because they commute, if you take out the local operations, there's not enough curvature to actually do anything. It's just like flat space, and this cancellation kind of depends on curvature. I do think what's neat is you can apply it to, if you have universal systems made from xy, xx plus yy, you can still basically do these things, which I was interested in a long time ago. So I'm going to, in the last bit of time, I'm actually just going to talk about work by Ed Barnes, because I think it's super cool. So if you may remember, at the beginning, I talked about how I had this picture of a unitary curve, which was just like a free-flowing curve. And then I immediately turned it into pulses. And for me, it's because at the end of the day, I'm a digital kind of guy, and it makes it easier to think about how the errors move. So Ed has like a nice set of work where basically he starts from just thinking about the curve, which is the control in 3-dimensional space. And the key components are the curvature, which is set by this control, and the torsion, which is, say, the detuning. And so you have the same key features, which is, if I look at the error in time, it also has to form this loop. And so if I close this curved loop, where I think of this epsilon as being my detuning error, because we always start with detuning errors because it's the most important error. In this first paper, he shows that you can continuously choose the curvature so it goes away. And if you make the curve in a way that the area vanishes, which again connects back to the difference between SK1 and BB1, I just have 2 areas come together, I can get rid of epsilon squared. And then this, I think, is a nice, like in this most recent paper, is that you can also fix the intensity error of the laser by thinking about the, by just thinking about the tangent vector to this curve. And if that tangent ends up going to 0, you can also cancel it out. And that sometimes forces you to have these higher dimensional suppressions. So you can use this a lot of ways. You can actually calculate what is the speed limit of a pulse that cancels detuning error to first order. like how fast can you do it and still get an angle. What's nice is the angle actually kind of, the angle of the gate you actually do comes from this little cusp here. That you can apply it, like all these things, to 2-qubit gates, multiple types of noise simultaneously. There's cool tools using synthetic robots to automate things. So then let's just look at how things could work in practice. So Ed and his collaborators actually applied it to IBM hardware. So you have this big superconducting qubit. Things drift over time, maybe. Frequencies drift a little bit. The pulses are some pulse you send in. Again, the qubit frequency is stable, control field stable, life is good. In reality, nothing's stable. Qubit frequency is not stable. Control field is not perfectly stable. Control field being unstable is also related to uncertainty in gate calibrations. And so you're trying to figure out what's the best way to do this. And then the thing is the same, right? You have the unitary you actually apply, U total. It's the unitary you want, U0, which is like the blue boxes. U noise is the red box. But now instead of building it in this discrete way, I actually build the whole thing in this analog continuous way. And I can write down this Hermitian operator theta 1 is basically the transformation, in this case, of the dephasing. Right? So this integration is, again, this integration over time. And there's some, So why can I do this integration over time and not have, and not worry too much about time-dependent operators? Because this thing is still small. And then we can find these controls that indeed take this error theta to 0, which makes the noise unitary identity. What's neat is it just relates to this tangent. So I integrate the tangent around, and I need it to go to 0. Because the tangent's a vector in 3D space, I can just do this closed curve condition. And it's nice. It just shows that we can robustly map these things to these geometric properties. So then they apply it to IBM hardware. They think about how to do the Hadamard gates. They find, sorry, of course, because it's on archive, it works better than the basic gates. But the most important thing is it should be more compatible to both detuning error and amplitude error. And notice how big this detuning error is. It's like 10% of the frequency of the qubit. So then what they do is they actually feed in these different errors and try to look at the performance where the dark purple ends up being like lower error, right? And these are these pretty cool 3-dimensional curves they generate to make these gates. And you see that in principle, in practice, it just becomes flat to amplitude errors at a fraction of a few percent and detuning errors at a fraction of a few percent. And that all can feed later into your quantum error correction if you want. But also, if I want to do analog quantum simulation or these hybrid quantum simulations, I can make these single qubit gates even better. Now, of course, I will just say, most places, right, we're not really limited by our single qubit gate performance. We're more limited by our 2-qubit gate performance, or maybe our measurement. But if you were limited, this would be a great way to make it better. And then I think what's amazing is it then becomes kind of a cool diagnostic tool where this question about what happens if you're not in your qubit space really comes into being. So if you're in the qubit space, life is super good. If you, in superconducting qubits, you have 0, 1, 2, this whole ladder of oscillator states. If you fall out during this circuit, it basically can't help you that much. And so you can see that it's actually a way, in the end, it also becomes kind of a way to measure leakage. So basically, by controlling the added error you find, you see some places there's not much leakage and things are fine. Other places you start to get more leakage as this error moves around. Okay. So actually, yeah. Any question? That's just my quick overview of Ed's work. I just think it's super cool. I think it's like the natural like progression of cool stuff going on in quantum control. I think it's also really beautiful because he does just map it to things like torsion and curvature. And so you can just use tools of geometry to like find good pulses that are continuous. Any questions? I know that was fast, yeah.
There are like 4 or 5 slides before where you're showing the different orders of errors.
Yeah.
So in the epsilon square term, it has like several nodes. Yeah, this one. But
Yeah.
so in the different planes, it has a different geometry.
Yeah.
So does it also use it, like is it also usable, like if you choose it, the different geometry using different planes to do the error corrections, so you can access like 4 states. Like you can access like 4 different.
That's right. Yeah. So I think what's yeah. So I think what's interesting is if I have a method to generate Hamiltonians for simulation. Anyway, in 2004, I took methods to generate Hamiltonians for simulation, turned them into composite pulses. You know, quantum signal processing, like Guang Hao, took better ways to do composite pulses, turned them into better quantum simulations, but still in a discrete way. This is neat because right now Ed is using these analog curves to generate better. They're no longer a composite, right? Like a continuous pulse, which gets rid of this error. And so I think this is what you're getting to. There should be a way to use this to more efficiently generate Hamiltonian simulations through continuous control of dynamics, is my guess. Am I way off?
So what I understood is like it's a working process to access the
Yeah.
different ways from one single.
Yeah, so no, these things work in, so I think what's, the point of this part is, like they design these pulses, and this is like, tells you what you're actually doing. But they design, and if you look at them in this trajectory space, they look like these funny cusps. And then they actually work. So they actually run them on real machines. Okay. Now, you may be saying to yourself, okay, you just talked about how to make gates better. Some of us believe that as soon as I have gates, I'm no longer doing analog quantum simulation. I'm doing digital quantum simulation. So one super cool paper that came out just this summer is, again, so I'm doing some kind of transformation where my Hamiltonian is starting in one spot, and then I'm changing my relative parameters, so it could be like I'm reducing the magnetic field, to see a quantum phase transition. And a key problem with quantum phase transitions, that's a problem. The thing which makes quantum phase transitions interesting is usually what happens is you start with a state of some multiplicity. Usually there's only one ground state. And then when you hit the quantum phase transition, 2 states become very close or even degenerate. So in the transfer sizing model, in the strong magnetic field, there's only one ground state. On the no magnetic field side, there are 2 ground states corresponding to all the spins up or all the spins down. Now these 2 ground states are separated by basically, in the Ising model, basically separated by a stabilizer, which is all the x's. So that the Hamiltonian commutes with the logical operator, which is all x's. So the Hamiltonian should never change the expectation value of that. So at the beginning, it's plus. And then as you're going down this, yeah, I'll just write this. Sorry, too much hands, not enough equations. So imagine you have, shockingly, this Hamiltonian. I'm just going to make J, yeah, make J of t, sure. And so what I'm going to do is I'm going to make a schedule. And then normally in this, they tie it together with just this S parameter. So we'll say B is 1 minus S, and this is S. And so B goes to 0, J goes to 1. But this Hamiltonian commutes with this logical X operator. So the value of this logical X operator should be the same. And because if I start in the all plus state, and so the ground state I get to on this side has to be this one. And if I and you know, I can think of this instead of being a logical operator as just being an X stabilizer. So this is one place where I think error detection is actually really compatible with analog simulation, because I can use error detection to see if I've fallen out of the symmetry space that I want to be in. And this is like a nice example. So if we go back to the slide, the side target state has two degenerate ground states. If we could, sorry, okay, great. So one of them is the negative one eigenvalue of XL. The other one's the positive value of XL. But because it's degenerate, I can pick any basis. So people usually pick the basis, which is one of them is all zeros, and one of them is all ones. But those two states are definitely not in the same symmetry space of our initial state. So what happens is as we're switching B to J, a small perturbation, in this case it's a magnetic field in the z direction, will mix those two symmetry spaces. So ideally, your experiment should get better and better when you go slower and slower. So in this plot here, all this is a theory paper. In this plot here, this t is how slow you're going. And this here is basically the fidelity of how good your final state is. And so things are bad because you're not adiabatic enough. Things start to get good because you get slow enough. Now you have this unwanted, and if you had no unwanted terms, things would just get better and better and better and better. But because you have these unwanted terms, if you do the naive ramping where you just slowly turn this up, maybe you try to go slower when you're close to where they're about to hit. Suddenly, as you go for longer times, the error gets worse. I think it's kind of cool is you sort of like overshoot, undershoot, and go back. Then you do see this continued improvement in the overall quantum simulation, meaning in this case that I remain in the same sector. But this piece here, in the paper, they actually call it an analog spin echo. So this is like the Hahn echo of making these phase transitions better. And so it's probably worth thinking about, well, what is the quadratic dynamic decoupling to make these phase transitions better? If there are other errors, can I use some of Ed's ideas on curvature of spaces to actually make the analog quantum simulation even better? And I don't know, but I think the answer is yes. And with that, I'm done. I'll take questions. Sorry, the robots. 1,000 other slides that I knew I wasn't going to get to. I'll just put up something nice to answer questions. Yeah, I'm going to do Quantum Center. It's great.
On the last part,
Yeah.
I wonder, is this pulse sequence or like composite pulse effective if you know already where you want to go, or it's very general and you cannot use it for any kind of Hamiltonian?
You need to know. In this let's see. No, it's pretty. That one looks pretty generic. I think we should look. We should think about some funny counterexamples. But basically, because the unwanted perturbation here is like a plus z term. Because it doesn't commute with this symmetry, somehow going over and then rolling back flips the way it's interacting, and it kind of like self-cancels, just like a spin echo. So probably you need some symmetry, which this thing doesn't commute with, to be able to cancel these kind of noises. That's my guess. But
Because naively thinking, like I was thinking, if you have anti-crossing before
yeah,
your target, let's say, regime,
that's right. That's right. Then you try to.
or also to cancel out, like kind of like having different.
Yeah, I think that's the right intuition. So, so if I'm doing some kind of adiabatic transfer generically, yeah. So let's say I'm trying to adiabatically go from here to here. Now the thing that goes bad is as I get to this close point, I could hop up to this other part. And so in some sense, like, so this is the schedule, right? Yes. Yeah, you kind of overshoot up to here. Then you roll back this way. But because of this expected error, right? The overshoot part will partly go up here, partly come back. And then when they come this way, loosely, this part, which will have to go back up here, will interfere with this side because they're now out of phase. And so the only thing that comes through is the bottom, if things were perfect. Yeah.
But that was my point. You have
Yeah.
to know where the anti-crossing is.
You have to have some sense of where, yeah. But I think what's interesting, I don't know enough details. I haven't gone into enough details. I think you can be kind of general near that point. Probably doesn't have to be exact at that point. And in their case, they're looking at, there's no anti-crossing, right? It's just like yeah. And then I think I'm out of time, so I will wrap up, but I'm happy to take questions later and see everybody for lunch. Great.
Great, thank you. Everyone is on break for lunch. Be back at 12:30.